Joker stole the Batmobile!
The Joker spread poisonous gas all over Gothamville South High School, and he stole the Batmobile. What are we gonna do?
We must stop the Joker and his evil plan to make students hate science. But what can we do?
I know. What if we have a science show?
Hi, I'm Lily Lonsbach, and this is Alice E., and welcome to the Lakeville South 2025 AP Chemistry Show. This is a science show. There will be chemical reactions, and I promise you, there will be fire.
As with all endeavors in STEM, there is an inherent risk in this show. But rest assured, the proper safety measures are being taken. This show invites you to become engaged in our world made of molecules, atoms, and ions. And we hope it will inspire you to learn more about our molecular world.
So let's brainstorm. How can we defeat the Joker and get the Batmobile back?
I have an idea. Maybe we could wish to a genie to bring the Batmobile back. Let's see Anna, Morgan, and Haley demonstrate their demo, Genie in a Bottle.
We need to get the Bat Genie to help us defeat the Joker. We'll be able to release it from this magical genie bottle. Morgan, will you give it a few taps and open it up?
Our magic genie actually uses some magic science. This bottle is filled with concentrated hydrogen peroxide, which breaks down into water vapor.
Hydrogen peroxide is used in many daily things, such as disinfectants and stain removers.
You can also see in the equation that in the formula, sodium iodide is written above the arrow, which means it is a catalyst. The catalyst speeds up the breakdown of the hydrogen peroxide into water and oxygen gas.
Watch as Anna and Haley do this again in a bottle you can actually see into. Sodium iodide is attached in a bag at the top of the bottle, and hydrogen peroxide is at the bottom. When combined, it makes a chemical reaction that creates water and oxygen gas molecules. This reaction is exothermic, which makes some pretty hot water. This water is water gas, and it looks just like a genie. Thank you for learning from our demo.
Unfortunately, it looks like the genie didn't grant our wish, but maybe Aline, Miguel, and Vincent can help us out with their ping pong popper.
Welcome to Gothamville Science Show. I'm Aline, and joining me are my fellow scientists, Vincent and Miguel. Today, we're excited to show you our ping pong demonstration using ethanol and combustion to create an exciting reaction. That's right, our demonstration will show how ethanol combustion can generate enough pressure to pop a ping pong ball into the air. Let's walk you through our setup. We have a small flexible flask with a small hole on its side with a small amount of ethanol. A ping pong ball is placed on top of the flask and covers the top to make sure the gas is trapped inside to build up the pressure. When we ignite the ethanol vapor using an electric spark on its side, the combustion will cause enough pressure to shoot the ping pong ball in the air. See our chemical reaction on the screen. Camera, please zoom in so everyone can see the setup before and after the reaction. Sometimes a bit of ethanol escapes during this reaction, and we may see a little bit of fire, but we have a lot of safety pieces next to us just in case. We have 5 of these set up, and we have about 50% success rate, so if these work, please cheer loudly. If it doesn't ignite right away, we'll switch to another one and hopefully get a couple to pop. Thank you, Vincent and Miguel. This is a great demonstration of how expanding gases can create motion. You can think of it as a small-scale version of the same principles used in engines or even fireworks. Thanks for watching our demo.
Wow, I'm feeling a little hungry after having to chase after the Joker.
Me too. Maybe Michael, Caden, and Matthew can share some Diet Coke and Mentos with us.
Hi, I'm Matthew, and this is Caden, and we're doing Diet Coke and Mentos. Today, we're going to share the science of nucleation. Camera, can you please zoom in on the small piece of candy known as the Mento? If we could continue to zoom in with the microscope, we would eventually be able to see millions of tiny craters or pits. These tiny spaces are a key to our demonstration today. Watch as we add one of these to a small glass of one of the most delicious treats life has to offer, a Diet Coke. Woo, this cascading fountain of bubbles is caused by Mentos that provide a nucleation site, also known as cracks or pits that allow the carbon dioxide gas in the soda to form bubbles that escape out the top of the bottle, causing the fountain of soda. Let's try a few different sodas. We have Sprite and sparkling water here to try. You may have only heard of Diet Coke being the soda for Mentos. This is because Diet Coke makes the biggest fountain due to its artificial sweetener, aspartame, which lowers the surface tension of the liquid significantly more than other liquids, allowing it to produce carbon dioxide bubbles quicker. Now let's try a larger demonstration. Thank you for watching our demonstration.
That was great, but I feel like we need something a little stronger, and no more snack breaks. I say we should try something a little more explosive.
Perhaps Daniel, Lisa, and Ellie's grain elevator explosion will do the trick.
Hi guys, my name is Lisa, this is Danny, and that's Ellie. Today we will be performing a grain elevator explosion using lycopodium powder. Lycopodium powder is a fine yellow powder from dried club moss plant, which is part of the fern family. The powder has a flower-like feel to it. First, you can see that lycopodium powder is not very flammable when it's just sitting there. But when you increase the surface area, the powder becomes very flammable, as you can see. So you might have heard, do not use flour to put out a grease fire. Well, now you know why. So sitting here is a grain elevator model. One thing we learned in chemistry this year is that if you increase temperature, then pressure will increase as well. So first, we're going to increase the temperature in the can by putting a candle into it. Then we'll put some lycopodium powder into the tube and quickly blow it into the tube to produce a large combustion reaction. Now that we have all the information, all the things that we need, what do you think will happen when we close the can? You're so right, Alice. Bear with us, because it might not work the first time. We have the second one here, just in case. Just in case. Yeah! Thank you for watching our grain elevator explosion, and guys, do not try this at home.
Maybe we can try freezing the Joker to catch him. We can borrow the power of liquid nitrogen, just one atom, then another nitrogen atom, then another nitrogen atom at a time.
You know, I'm not sure if this is going to work. You can never really trust an atom. They make up everything.
Anyways, let's ask Carter, Cassie, and Finn to show us some tricks with liquid nitrogen.
Testing. Oh, it's on. It's on. Hi, guys. My name is Carter J. Windorf, and this is Cassie and Finn. And we are the amazing wizards from Gothamville South High School to show you some super cool magical science. Cool as in negative 196 degrees Celsius or below negative 300 degrees Fahrenheit. Cassie is quickly going to pour some liquid nitrogen from this tube thing into another one. Now, I know you're all good-looking people, but you need to be good at looking and see the bubbles forming in this liquid nitrogen. Those bubbles are actually nitrogen moving from its liquid phase to its gaseous phase. You may also notice that the liquid nitrogen is so cold that it freezes the water vapor in the air. This liquid nitrogen will freeze the water, and at the same time, the violent boiling of nitrogen throws up tiny bits of water, like a frozen mist giving a fog effect. Finn, if you could quickly blow on it. Ooh. Next, we're going to use the liquid nitrogen to make some things cooler. Since flowers are mostly water, Dipping a flower in the liquid nitrogen freezes all the water, causing the flower to become dry and brittle. Watch as Cassie takes out the flower and jumps it on the ground. It breaks. This is because the molecules in the air are less energetic, causing them to take up less space. This lowers the pressure inside the flower to become below normal air pressure, causing it to shrivel. Now Finn is going to do the exact same thing, but with a blown up plastic balloon. Since the air is so cold, the particles in the balloon will stop moving, which will cause the balloon to actually shrink. And the more oxygen that comes back into it, it'll continue to go up. So you all know that the tea kettle makes a whistle when it boils, but what actually makes that whistle? Pressure builds up and the steam has nowhere to go except through the hole in the lid. When enough steam has been created so that it rushes through the hole, causing the kettle to whistle. Wow, that's different. The same thing happens with liquid nitrogen. It's actually boiling, producing nitrogen gas, and is forced out through the hole, the same way the steam from the boiling water is. I hope you learned about some cool science today. Thank you so much.
Maybe we can also make the Batmobile glow in the dark to find it faster. I think that's my bad. It's getting pretty cold in here, as we can see. So I think it's about time we turn up the heat. Which, speaking of which, why do chemists like to play with fire?
I'm not sure. Why?
Because they enjoy a good reaction.
Let's see combustion in action with Kennedy, B, and Hannah's whoosh bottles demo.
Hi everyone, I'm B, and this is Jack and Hannah. Batman needs our help with the Batmobile. We need to help him figure out which fuel has the fastest flame speed. Flame speed refers to how fast a flame can burn off fuel through the gas and vapors, not the liquid. Our whoosh bottle experiment models the small explosions that occur inside a car engine. The speed of the flame is very important. Too slow, it won't push the piston into the engine. Too fast, it could explode. Please zoom in on the table. We coated these bottles with the alcohols, 70% isopropyl, 70% ethyl, 95% ethyl, and 99% isopropyl. Jack will carefully drop a match into the bottle, and we will be able to see how fast the flames ignite. Please dim the lights. Let's start with 70% isopropyl and work our way over to 99% isopropyl. That first one was pretty good, but let's see if we can find a faster flame speed for Batman. Now Jack's going to try to burn the 70% ethyl alcohol. Pretty fast, but I think we can get it faster. Let's burn the 95% ethyl alcohol. That was pretty fast, but we have one more we need to try. Let's try the 99% isopropyl alcohol. That looks super fast. Let's try it again. That one was definitely the fastest. Now we can tell Batman to use the 99% isopropyl alcohol to move the Batmobile the fastest to save Gothamville High School.
All right, guys, this time I actually think we should make the Batmobile glow in the dark so we can find it faster.
That reminds me, what did the photon say to the bellhop when he offered to help with his luggage?
What?
He said, "No thanks, I'm just traveling light."
Oh man, that joke wasn't very bright, but you know what is? Tegan, Ellie, and Alyssa with their luminescence glow demonstration.
Luminescence is when something gives off light without getting hot, like how a firefly glows in the dark. This natural light is called bioluminescence, and it happens because certain chemicals inside the firefly's body react with oxygen to produce the light. But luminescence isn't just found in nature. We use it in technology too, like glow-in-the-dark toys, jewelry beads, and fishing lures. These items store UV light energy by the movement of electrons from the ground to an excited state and in reverse. Whether it's in nature or human-made, luminescence is a cool way for light to shine without heat. We have 5 different examples for you today. First, Tegan and Ellie have some glitter bug lotion on their hands. Please dim the lights and the UV lights will be turned on, also known as a black light. Lights up, please, UV lights off. Second, we have 4 different solutions that emit luminescence when exposed to UV light. Ellie has yellow fluorescence and pink rhodamine. Tegan has clear tonic water and orange luminesce. Watch these change in the UV lights. Dim the lights and turn the black lights on, please. Lights up, please. Third, we have these UV-sensitive beads. These contain phosphors that change color when exposed to UV radiation like the sun. But we have a black light here today. Camera, zoom in, please. Notice the multicolors and how they changed. Fourth, I hope you guys are ready to play a game. We have a luminescent word game where you have to guess the missing letter. Lights down, please. What letter are we missing? Yes, and what does this spell? Lights up, please. And last, we have a chemiluminescence demonstration called energetic light. Camera, please zoom in on the beakers. In the beakers, we have potassium ferrocyanide, and in the other one, we have a mixture of fluorescein and luminol, 2 substances that luminesce via a redox reaction. After we make sure the camera is zoomed in so you can see the reaction, we will ask for all the lights to go down, including our black lights. Ready? 3, 2, 1, lights out and pour solutions. Perfect. A great glowing solution that will help us light the path to finding the Batmobile. Thanks for sharing our illuminating reactions.
Wow, I feel enlightened after that one. Alice, are you ready to launch into our next demo?
For sure. Next up, we have Kelly and Leah with their Alka-Seltzer rockets.
Everyone, my name is Leah and this is Kelly. Today we will be creating Alka-Seltzer rockets to distract the Joker. Before we start our demonstration, I would like to warn the people in the first 2 rows as some of our canisters may launch farther than expected. In this experiment, we will be using Alka-Seltzer. Camera, please zoom in. It is an antacid that helps with an upset stomach, indigestion, and heartburn by lowering the acidity of your stomach. It is made of sodium bicarbonate, more commonly known as baking soda, and citric acid. This is an acid-base reaction, and when it reacts with water, it creates sodium citrate and carbon dioxide gas. In this experiment, the product we care about the most is CO2 gas. As it builds up, it will eventually create enough pressure inside the film canister to eventually pop the tube off. To create this reaction, we will film a film canister about 1/4 full of water and then drop in an Alka-Seltzer. Quickly seal the cap and flip it over. Now let's see how this works on a larger scale. We have a whole whiteboard full of canisters that are ready to react. Kelly just flipped over the whiteboard, and so please be patient as this may take a second. And so while we wait, Kelly has some jokes to tell.
All right, let's go. How do rockets party? They plan it. What's a rocket's favorite candy? Milky Ways. Why did the rocket get an award? Because it was out of this world. Hey, why did the astronaut break up with his girlfriend? He needed some space.
We hope you guys had much of a blast as we did.
Well, I think this next experiment is really going to blow our socks off. Trust me, my ideas are fireproof. They can't be extinguished.
Let's see Carter, Lane, and Casey's combustion of acetylene.
Hi, I'm Lane, and I'm here with Carter. Today, our main chemical we work with is calcium carbide. That is a chemical structure of CaC2. which makes acetylene gas when mixed with water, represented by C2H2 structure. Now, if you look at the screen above, you will see how this reaction will work. When we put calcium carbide into water, it will produce acetylene gas. And when that gas mixes with oxygen from the atmosphere, it combusts. This will end up creating carbon dioxide and water vapor while releasing energy along the way. We'll perform this experiment on a smaller scale to demonstrate how it works. Sometimes our first try doesn't work out exactly right, so we have a couple extra bottles ready to go. Carter will add a single scoop of calcium carbide into the Gatorade bottle, and Carter will put a towel on top to keep the acetylene gas inside. Now when we are ready, Carter will use a lighter through a small hole in the bottle to light the gas on fire. A quick warning, this might be loud and you might want to cover your ears. Wow, that works so well, and it was only this small scale. I think we should try making it bigger. As we have seen, acetylene gas is extremely flammable. A common use for it is in welding, where it can be seen producing the hottest flame of any common fuel gas mixed with oxygen reaching 6,000 degrees Fahrenheit. It looks like our next cannon is almost ready. Let's see how this reaction works when we put way more calcium carbide into the bottle. Looks like we got a little fire. We're just gonna put that out. Put it around, yeah. All right. What? Where's the giant explosion, you might ask? Well, when we put more calcium carbide in the bottle, it produced more acetylene gas. The extra acetylene gas pushed all the oxygen outside of the bottle. When there's little oxygen present, the reaction doesn't work nearly as well. This is why you see a flame appear outside of the bottle where the acetylene gas is trying to react with the oxygen. Now that we are well experienced, let's go back down to one scoop so Batman can learn how the Joker's bombs work and we can all try to save Gothamville together. This one might be loud. Okay, let's count down from 5. 5, 4, 3, 2, 1. 1. Wow, this experiment was really the bomb. Thank you for all your attention.
We still need an alarm to alert all the students of Gothamville South when we find the Batmobile.
I know a few people who have pretty sound ideas. Let's see how Grace and Cash use liquid nitrogen, so make some noise.
Have you ever wanted to see what happens when things get so cold they freeze almost instantly? In this experiment, we'll be using liquid nitrogen, which is colder than anything you can imagine, around negative 196 degrees Celsius. We'll be testing how the supercooled liquid affects different objects, showing how materials can change when exposed to such extreme temperatures. From shrinking to freezing to creating unexpected reactions, liquid nitrogen will help us explore the science of temperature. When we put this bouncy ball in the liquid nitrogen, the low temperatures cause the ball's material to become much less flexible and more brittle. This is because the atoms inside the ball slow down and lose energy, making it lose its ability to deform and return to its original shape after impact. So instead of bouncing, the ball might crack, shatter, or just not rebound when dropped. Now we'll do the same with a marshmallow. But due to the difference in the marshmallow's structural composition, the effects of liquid nitrogen will happen more quickly. Next, we'll pour liquid nitrogen into a flask and seal it where the only way for the gas to escape is through a horn. Liquid nitrogen evaporates into a gas at room temperature. Shaking the beaker accelerates this evaporation, causing it to evaporate quicker, building up the pressure inside the sealed flask. The higher the amount of pressure in the flask, the more it will vibrate and produce louder sound as it escapes through the horn. Thanks for learning more about liquid nitrogen with us.
I don't know about you guys, but I am fired up about this next experiment.
I agree. I think it's going to be really cool.
The Joker is skating across Lake Marion with the Batmobile. Maybe Julia and Jordan can light it up to capture him once and for all.
All right, Jordan, how are we going to stop the Joker? I think we should just light Lake Marion on fire.
But, Julia, how are we supposed to light Lake Marion on fire? It's completely frozen as ice.
Well, we have chemistry for that. Right here, I have 2.5 grams of calcium carbide. When it comes into contact with water, it'll produce acetylene gas, which is highly flammable, and you can see the reaction right up there on the screen. When I put it onto the ice today, it's going to react and produce the gas, which then Jordan will light, and it'll produce a flame.
Calcium carbide has real-world uses too, such as in the production of acetylene gas for welding. It has a very high melting point, making it perfect for cutting and joining metals. Julia will now add the calcium carbide to the ice, which will start the reaction. This is tricky because we want it to melt just enough to produce acetylene gas, but not enough for it to all escape into the atmosphere.
Can we dim the lights, please? All right, now that we successfully lit this small amount of ice on fire, let's move on to a bigger scale to see if we can successfully light something as big as Lake Marion. We'd like you guys to cheer loud if we're successful. Thank you for watching our demo.
Okay, so we did light it up, but unfortunately it all went up in smoke.
Uh-oh, it looks like the Joker's trying to hide in all of this hazy fog.
Hopefully Michelle, Bay, and McKinley can clear things up with the bat signal and their smoke rings.
Hello everybody, I'm Bay, this is McKinley, and this is Michelle. Today we're diving into some super cool science, Batman style. We're talking about smoke rings, but not just any smoke rings. We're releasing bat moles into the air. Now you might be thinking, what's a bat mole? Good question. In chemistry, a mole is just a way to count a huge number of tiny particles. And in Gothamville, we all know the bat signal works best in a cloud of smoke. So today, we're combining science and superheroes to create an ultimate bat mole smoke rings. We have 4 key tools here. We have a liquid smoke machine in the back, because how else are we supposed to make Gotham-style fog? And then we have cups, small but mighty like Robin. And then we have 5-gallon buckets, the Batmobiles, the smoke rings, and then a garbage can, because even Batman needs to clean up Gothamville. Now, if we could have the lights turned on. Here's how this works. We fill our containers with smoke. We hit, tap, or slap them like Batman taking down a bad guy. Boom, smoke rings fly out, smooth and perfect, like the bat single calling for help. Now, why does this happen? It's Bernoulli's principle. When we push air through a small round opening, that just slows down while the center speeds up. That's science talk for basically a donut. But imagine this in Gothamville. Batman's up on a rooftop, and instead of a boring old bat signal, Commissioner Gordon just smacks a giant bucket and sends up a perfect smoke ring. The Joker sees it and knows it's over for him. Now you're probably wondering why this matters. It isn't just for fun, although let's be real, it's pretty awesome. These vortex rings happen anywhere, in jet engines, volcano eruptions, even the way dolphins play in water. So the next time you see Batman disappear in a cloud of smoke, just know he's using some high-level physics. Now, let's fire up the bat machine and make some smoke rings. Who's ready? Now, the big signal that Commissioner Gordon uses to alert our hero Batman. Now, the Batman's in action to round up the Joker. Thank you for tuning in.
I have an idea. What if we use that element of surprise to catch the Joker?
Let's see if Joey and Logan can help us out with their disappearing alarm clock.
Hello everyone, my name is Joey Finch and this is Logan Kieran, and today we'll be showing you the silent alarm clock. This is a vacuum chamber. Camera, please zoom in. When a marshmallow is placed inside a vacuum chamber and the air is removed, the marshmallow expands significantly because the pressure inside the chamber becomes much greater than the decreasing pressure surrounding it, causing the marshmallow to inflate outwards to fill the space with its internal air pressure. Basically, Boyle's law, picture on the left, states that the marshmallow's volume expands to try to equalize the pressure difference between its interior and the vacuum around it.
This is an alarm clock. How pleasant. I know you are all jealous and want one of these to wake up to. Now, when placed in a vacuum chamber, an alarm clock will still physically function and appear to be ringing, but you won't hear the alarm bell sound because sound waves cannot travel through a vacuum, as there are no air molecules to vibrate and carry the sound. You may still feel some of the vibration as the clock is in contact with the base of the vacuum chamber, but little to no sound. So, essentially, if you scream in a vacuum chamber, no one will hear you. So, when we suck the air out from the chamber, it may take a little while. Technical difficulties. That was not a joke. We're turning it on again. Second gear. We can see that the alarm is still ringing, but there's a lot less sound. This is because there are way less air particles for the clock to push on. Hopefully, Batman will be able to make use of this device and surprise the Joker. Thank you for joining us on our demonstration.
Wow, I can't believe that alarm clock just disappeared.
Right? But unfortunately, the Joker still has the Batmobile.
Maybe Trinity, Ellie, and Christina can stop him and the Batmobile with an intersection.
What do you mean, an intersection?
Well, when you see the signs, stop, go, and boom.
Hello, I'm Ellie, this is Trinity, and this is Christina, and today we will show you 3 demos in a row. Have you ever used hydrogen peroxide to clean out a cut, baking soda to bake cookies, or dish soap to clean dishes? The power of fire and pressure and how they interact when confined in a small space. Using just matches and flasks, we're going to create a reaction. In our first flask, we have sodium bicarbonate and acetic acid. Christina has added the baking soda, and Trinity is going to bring the flaming splint into the flask. And it goes out. She's going to do it again. The carbon dioxide produced does not support combustion. That should stop the Joker from any silly flaming tricks. In our second flask, we have hydrogen peroxide and sodium iodide. Trinity is going to bring the extinguished piece of wood into the flask. Go. See how it reignited the flame? Okay, so the oxygen in the flask supports combustion just like oxygen supports combustion in the real world. Any fire needs fuel, oxygen, and heat. This provides the oxygen. That'll light up the Batmobile. In our third flask, we have hydrochloric acid and metal zinc contained. This creates a hydrogen gas, and we're trapping this in the bubbles off to the right. Trinity is going to bring the splint into the flames. Boom! Thank you.
I'm so confused about calculating density. It's mass confusion.
Lily, it's not mass confusion, it's mass divided by volume.
Here are Caleb, Carter, and Wyatt with temperature, inversion, and density.
Hi, my name is Wyatt, and I'm here with Caleb and Carter. Today we're doing 2 experiments about density. Density is a substance mass divided by volume, as you can see on the density triangle above. For the first experiment, we need your help. We want you to tell us if you think the pop will float or sink in this tub of water. First up, we have Diet Coke. As you can see, it floated. Next up, we have Coke. It sunk. Next, we have Sprite. That one also Diet Pepsi. Diet Pepsi floats. Lastly, we have Sprite Cranberry. As you can see, it sunk. Why did this happen? Where Diet Coke and Pepsi floated, but the others did not. The answer is density. The added sugar, aspartame, to the Diet Pops have a smaller density than water, which has a density of 1 gram per milliliter, while the other have higher density than water, causing them to sink. Now for our second experiment, we test the density of water at different temperatures. As in the hot glass, in the yellow water, there's warm water, and in the cold water, there is blue. Brutal. Caleb will now put the hot water on top of the cold water with just a card separating the two. As you can see, when he removed the card, there was minimal mixing, and that the yellow water stayed on top and the cold water stayed on bottom. Now we would try this again, where Caleb puts the cold water on top of the hot water. As you may notice, they start to mix, turning the whole solution green. You might wonder why this happens. The answer is also density. Water doesn't always have a density of 1 gram per milliliter. As we said before, the substance can change density when temperature changes. Boiling hot water has a density of about 0.958 grams per milliliter, while cold water has a density of 1.0. This causes hot water to float to the top and cold water to sink to the bottom. A place you may see this in the real world is a lake in the summertime, where the warm water stays around the surface and the cold water is at the bottom near your feet. Hopefully this green mixture can help us create a poison to save our school from the Joker. Thank you for listening to our presentation, and hopefully you learned something about density.
I can feel it. We're almost at the Joker's hideout.
Next up, Tegan, Molly, and Lucy are going to burst onto the scene with their methane mamba bubbles.
Hi everybody, my name's Tegan, and inside this tank we have some methane gas. Methane is great for fueling things like your furnace, which heats your house, or a power plant that makes electricity, but also fire. Surprise, this experiment uses methane to do some totally fire things. Get it? First, I'm gonna need a couple of helpers though. Molly and Lucy, come closer so we can get started.
I don't know how I feel about fire. Do you mind telling me what's going on?
Sure, in this methane mamba experiment, I'm gonna use some methane gas to light Molly's hand on fire.
How are you going to do that without burning my hand off?
Easy, follow me. In this bucket here, I've got a mixture of soapy water, perfect for a bubble bath. This mixture is just water and dish soap, so not only will Molly's hands be on fire, she also have very clean hands. This soapy water will create a thin layer on her skin and prevent direct contact with the fire. When the methane comes in direct contact with the bubbles from the soap, the fire burns off quickly. The hose that connects our methane is bubbling through soap and forming a scary snake tower, perfect for scaring off the Joker. Water can also make it grow and move like a snake, which is even scarier. These bubbles float because the methane gas inside the bubbles is less dense than the air, which is mostly nitrogen. Lucy, take these bubbles and scare off the Joker with a fireball. Now Molly and Lucy, for the really scary part, scare off the Joker with your hands of flames. Methane's chemical formula is CH4. Its molar mass is 16 grams per mole, whereas nitrogen, N2, which makes up most of the atmosphere, is 28 grams per mole. This is why the bubbles filled with methane rise, because they are less dense than the nitrogen. The chemical reaction above displays the combustion of methane and shows the products, which are CO2 and H2O. Nice job, guys. You demonstrated how methane gas reacts with fire, and you did it while staying safe.
Wow, I really thought they were going to be able to catch him. Maybe with the help of Eric, Todd, and Quentin, we can speed up this process with their rapid vacuum acceleration.
Our demonstration consists of a 9-foot long PVC pipe tube that we shoot a ping pong ball out from this side into this Dr. Thunder can. We use these aluminum foil sheets to stop any air from coming into the vacuum we create with this vacuum pump right here, which sucks out all the air from the inside. This could be a little bit loud, so you might want to cover your ears. As you can see, we punctured the aluminum foil on this side, and all the air in the atmosphere pushed into the vacuum, pushing our ping pong ball through this can over here. Thank you for learning about ping pong ball acceleration.
Wow, because we lost the Batmobile, we are really stuck here.
Yeah, stuck in a sticky situation.
Here's Emmett, John, and Hudson with their sticky boards.
Hello everybody, I'm here with Hudson and John, and today we're going to be performing some magic tricks. Hopefully it'll help save Batman from the Joker. First, here's John with his magic wand. Watch as he performs his first trick. Wow, thanks for sprucing up the place. Now our second tricks involve the two chemicals above on the screen. One, barium hydroxide, and is in the beaker Hudson's holding up. As you can see, it's just the beaker, nothing on it. The second ionic compound, ammoniothiocyanate, is added to the beaker, and Hudson and John are preparing the two mixtures at the same time for us. They are performing the mixtures on top of wood they found outside and is still wet. Now as they mix these beakers on top of the boards, I want to tell you a bit about the reaction. This reaction creates some ammonia, a smelly gas at room temperature, whose formula above, NH3, is a weak base, but quite reactive and is used in refrigeration systems like ice arenas and is a fertilizer for agricultural uses. Guys, can you smell it? Sorry guys, it's all in the name of science. Also, you will notice behind our chemical reaction is triangle H. This is known as the enthalpy or heat at constant pressure. It indicates the reaction is endothermic, meaning it takes in energy. Are you guys ready? All right, let's see it. No? Well, positive enthalpy means that the energy from the surroundings is taken in by the system of chemicals and the energy is removed from places like the beaker and the board. Barium hydroxide is a strong base and is quite a solid caustic base, similar to drain cleaner, ammonia. Are we ready now? All right, let's see it. Wow. So how did we do it? The chemical system took in so much energy that it removed enough energy from the water on the board to make it change from liquid to solid, freezing the water and freezing the beaker and board together. Some nice chemical magic, huh? Thanks for learning a little bit about endothermic chemistry today.
All right, guys, nothing special. Up next is a 10-minute intermission. Feel free to get up, get a drink, take a stretch, anything like that. See you in 10 minutes.
Oh, I'm thinking of 6 hour when you guys had to go later. Oh, that's on. That's on. Wow.
Ooh.
Introduce yourself.
Hello, everybody. I am Danny Gonzalez, Boy Wonder.
And I'm Carter J. Windorf, and we'll be your host tonight.
So, we all welcome you to the Lakeville South High School 2025 AP Chemistry Show. This is a science show, and I'm guessing all of you are used to the fact that we're doing reactions and that there will be fire.
While most of you have probably heard us complain about AP Chemistry at some point this school year, we actually do like the class, and we are excited to show you some of the great things that we can do.
So, let's begin with how do we think we're going to defeat the Joker and get the Batmobile back?
I don't really know, but I think we could start by trying to go in disguise. Maybe Anne-Marie and Noah have an idea for us?
Hi everyone, I'm Anne-Marie.
And I'm Noah. We will be demonstrating how helium and sulfur hexafluoride can disguise our voices.
As you all know, most balloons contain helium inside of them. Helium is less dense than air. Air is composed of almost 80% nitrogen, which, as you can see above, has a molar mass of 28. Helium's mass is 4.
These numbers show helium is much less dense than air. So when you fill a balloon with helium, it will make it go up and rise.
However, you can also fill a balloon with sulfur hexafluoride, which will make the balloon fall. With a molar mass of 146, it is like a lead balloon.
First, Amory will show you the effect of helium.
Hello everyone, and welcome back to the show. This year our theme is Batmobile. A mole is a counting unit equal to the value of 6.02 times 10 to the 23rd.
As you just heard, her voice got super high. This is because helium is around 6 times less dense than air. So since there is less resistance, her vocal cords are able to vibrate faster, causing her voice to go higher.
Now Noah will show you the effect of sulfur hexafluoride.
I hope you all enjoy the rest of our show and help the students of Gothamville South get the Batmobile back from the Joker and stop his evil scheme of making kids hate science.
For Noah, since sulfur hexafluoride is 5 times more dense than oxygen, her voice got deeper, unlike mine, which got higher. Because the gas is so dense, it causes the vibrations of sound coming from her voice box to slow down, making her voice a much lower tone.
Now we are able to disguise our voices to help us defeat the Joker.
Batman! Thank you for watching our demo.
Wow. Thank you for showing us that crazy disguise by changing your voice.
Yes, sir. We can definitely rely on those disguises. But we're going to need to actually find another way to beat him.
Well, let's welcome Caden Bigelow, AJ Jordan, and Anders Clement to show their sock cannon idea.
Woo! Hello, my name is Anders Clement. I'm here with my partners Caden Bigelow and AJ Jordan. We're going to show off our plan to defeat the Joker. In order to defeat the Joker, we're going to use our calcium carbide bat cannon. You might be wondering what calcium carbide is. If you look at the formula above, you'll see that calcium carbide combines with water to produce acetylene gas, C2H2, and calcium hydroxide. What we're interested in is the acetylene gas, which when ignited with a lighter combusts, producing carbon dioxide, water, and a large explosion, which we'll use to propel this sock. The gas is mostly used in welding today since it burns very hot. The massive exothermic reaction produces a large amount of heat and light, which is great for melting and welding metal together. If you please follow us to the middle of the stage and turn the lights up.
First, we will load our projectile, the bat sock, into the bat cannon. Next, we will put the calcium carbide into the bat cannon. Finally, we will add about 3 milliliters of water and wait about 20 seconds.
The cannon should be ready in about 20 seconds, and when Caden puts the lighter at the hole at the bottom of the cannon, it should shoot off and hit the Joker. To ensure we're being safe while shooting off this cannon, we all have safety glasses on. You might want to cover your ears because this is going to be loud. And if we miss, please boo. 3, 2, 1. Oh, looks like we missed the Joker. We got to go back to the Batcave to find something else to do.
Wow, that was pretty dramatic, and we got our shirt hit, but it wasn't enough to stop the Joker.
Wow, you Debbie Downer. We're just trying our best over here. We're all students anyways. We need to have fuel, though, to make sure that we can fight against the Joker. So let's see what Daniel, Hallie, and Annika have for their idea with the strawberry float.
Woo! Batman, after a long night of battling Gotham's villains, returned to the Batcave in need of a refreshing treat to recharge. Even Batman deserves a delicious strawberry float to keep him energized. In this beaker, we've mixed 300 milliliters of water with sodium bicarbonate, commonly known as baking soda, and a bit of Elkinox, a type of soap. To give it that vibrant orange hue, reminiscent of orange juice, Daniel is adding 100 milliliters of methyl orange indicator.
But Annika, that's not a strawberry float.
You're right, Hallie, it's not. So here's where the power of chemistry comes into play. Just as Batman transforms to meet any challenge, we'll transform this orange juice into a strawberry float. By adding hydrochloric acid to this mixture, a chemical reaction occurs producing carbon dioxide gas. The carbon dioxide gas gets trapped in the soap, creating a frothy eruption, much like a bubbling strawberry float. This is called an acid-base reaction. The hydrochloric acid, our acid, reacts with the baking soda, our base, to produce sodium chloride. Then the methyl orange indicator changes color based on the solution's pH, shifting from orange in a basic environment to red in an acidic one. And this is something we see every day. For example, when acidic ingredients react with basic ingredients in baking, it produces carbon dioxide gas, causing things like cakes and bread to rise. Now, please zoom in on the beaker and let's make a strawberry float.
Now Batman can enjoy a sweet treat and save the city.
Thank you for joining us and learning about some acid-based science.
That was so good. But I think it's time everyone hears an awful chemistry joke.
Sounds right.
What do you call an educated tube?
I don't know.
A graduated cylinder.
Should have seen that coming. Oh, man. Let's just skip to science, huh? How about we get to actually find a way to get to the Joker through more firepower? Let's give it up for True, Chloe, and Monsi with their new rocket science idea.
Hi, my name is Truk, and I'm here with Chloe and Monsi. Batman needs more fuel to fight off the Joker, and this sprinkler explosion will give him a quick energy boost. The explosion could happen anytime from the moment the can is lit, or up to 60 seconds, or it might not happen at all, so keep your eyes on the Pringle can. This will be loud, so you have sensitive ears, you might want to cover them. Can we please have the light dim and camera zoom in onto the flame? Here's how it works. The inside of the Pringle can is filled with hydrogen gas. We lit it, and then oxygen from the air mixes with hydrogen, and as the flame we lit reaches to the inside and burns off hydrogen, oxygen and hydrogen react in a combustion reaction, creating an explosion. Once again, it would be loud, and also to keep your eyes on the Pringle can. Okay, here's some jokes. What's a Pringle can rocket's favorite exercise? High intensity combustion training. Why don't Pringle can rockets ever win arguments? Because it had too many explosive tendencies. All right, thanks for joining us.
Incredible nitrogen. Wow, that was something. But now we need to think about how we'll get into the Joker's lair.
We're going to need to strategize a way through the cover of darkness. Let's see if Lily and her sidekick Alice can show us a way to get under through their genius plan of liquid nitrogen.
Hi, I'm Lily.
And I'm Alice.
Inside of this cooler, we have liquid nitrogen, which is the compressed form of nitrogen gas. Nitrogen gas makes up about 78% of the atmosphere around us. The boiling point of nitrogen is so low that it is boiling, bubbling, and turning into gas at room temperature. It is also really cold, so we have to be careful not to touch it with our bare hands.
But what if I did put my hand in it? Either way, I think we could probably use it to stop Joker and get the Batmobile back.
But maybe we shouldn't put your actual hand in it.
Well, what could we use instead?
Oh, I know. We can just use this fake hand.
Sure. Well, while we wait for that to freeze, let's make some frozen liquid nitrogen bubbles. They could probably slow down the Joker and stop him in his tracks.
Good idea, Alice. First, let's mix together some dish soap and some tap water. We have to make sure the tap water is very cold, though. Next, let's add a big scoop of our liquid nitrogen and pour it into our soap and water mixture. Let's watch as the bubbles get really big and eventually freeze up. Once they're frozen, we should be able to get the Batmobile back.
Hey, can I pop one of those bubbles?
Yes, as a matter of fact, the bubbles are only freezing because of the cold temperature of the liquid nitrogen. So, if you pop one, you should be able to see a cloud of nitrogen gas appear.
Hey, that was really cool.
What happened to our hand, though? Wow, it looks like the negative 196 degrees Celsius temperature of the liquid nitrogen has frozen the hand. That means it quickly transfers, oh my gosh. Good thing we didn't put your actual hand in there.
Yeah, thanks for coming to explore liquid nitrogen with us.
Well, that was pretty violent, but I think we need to lighten the mood with maybe another chemistry joke.
Good idea, sir.
What did the chemist say when he found a gold mine?
I'm not sure. What do you guys think?
This is definitely an element of surprise. Please welcome up a million different people, Jack, Oscar, Ethan, Oliver, and Presley for their Roy G. Biv reaction.
Woo! Hey scientists, welcome to Batman's Science Lab. Today we're exploring color-changing liquids, kind of like the gadgets Batman uses in his crime fighting. These liquids may look like magic, but they're all about chemistry. Let me show you how it works. We're using a very dangerous chemical called formaldehyde to create this reaction. But don't worry, it's safe in small amounts and with safety goggles like ours. 3, 2, 1, pour. So, what's happening here? We're using a process called an acid-base reaction when the substances undergo a neutralization reaction with a buffer solution forming, holding the pH fairly steady for about a minute. Then, the buffer breaks, and we see the colors appear as the pH rapidly changes. You will see the changes going through the rainbow, Roy G. Biv. Red, orange, yellow, green, blue, indigo, and violet. This reaction happens in a specific order, kind of like Batman's perfect timing when he's tracking down a villain. Let's try this other reaction using phenolphthalein, water, and ammonia to make sense of what is occurring. Inside this beaker, we have a colorless solution of water and an indicator called phenolphthalein. This indicator is colorless in water and acidic solutions, but turns pink in the presence of a base. Watch as Presley adds some drops of base. Nice job, Presley, dropping the bass on that demo. Notice the bright pink color. This is what you will notice during our next 7 reactions, making a rainbow. While we wait, we thought we should give you a few chemistry jokes. Hey audience, what do you do with the sick chemist? Well, if you can't cure him and you can't heal him, then you might as well bury him.
What are you doing?
Tell you what, Jack, I was telling some pretty stellar chemistry jokes the other day, and I couldn't get any reaction.
Good one, Ethan. That was a real neon slapper.
As you can see, the 7 reactions have created a rainbow, and these chemicals reacted at specific times so Batman can use science to stay one step ahead. Remember, always stay safe with chemicals, and thanks for looking inside Batman's Science Lab.
Wow. Absolutely mind-blowing. Oh, sir, I just got news that Robin got poisoned.
Well, we're going to need Robin to be able to fight against the Joker, and I know just the person to call. We need Mom to the rescue right now. Do you think Lena and Sarah could help us?
Hey Gothamville citizens, I'm Lena and this is Sarah, and today we're diving into a high-stakes experiment to battle one of the Joker's plans, upsetting Robin Hood's stomach with a little chaos in his food. Robin Hood says his stomach feels like it's on fire, so today, Mom will be coming to the rescue.
Mom? What do you mean? Lena, our moms are in the audience.
Yeah, Sarah, you're right. And although they're amazing and can fix a lot of things, what I mean by Mom is milk of magnesia. It's a common antacid that will help soothe Robin Hood's stomach. Here we've got a powerful acid, just like the nasty chemicals the Joker might sneak into Robin Hood's food. The acid is too much for our stomachs to handle, but fear not, because where there's chaos, there's always a hero ready to restore balance. The normal pH of a stomach is 2, and this is what Robin Hood's stomach looks like before he eats the nasty food that the Joker contaminated. Let's enter in our milk of magnesia. All right, now let's see what happens to his stomach when he eats the acid. As you can see, it turns red, meaning his stomach has turned highly acidic. But let's wait and watch. And there it is. The base has been neutralized and the milk of magnesia returns to its original state. Just like Batman doesn't let Gotham's peace falter, milk of magnesia ensures that your stomach is back to balance, fighting off excess acid and restoring order. Let's try one more time, Sarah. Milk of magnesia is like the Batman of the digestive system, neutralizing acid, saving the day, and bringing balance to chaos. So next time your stomach is under attack, don't let the Joker win. Reach for milk of magnesia and restore balance before the chaos takes over.
Wow, sir. That was quite delightful. I think Robin isn't back in stable condition, thanks to our moms being awesome superheroes.
Wait, I'm getting notice that we need another awful chemistry joke. Why did carbon marry hydrogen?
Why?
Because they bond well. Please welcome on up Cade and Grant to develop a serum to intake all the gas and evaporate it.
Woo. Hello, I'm Grant, and this is Cade, and this is Styrofoam Head Hugo and Harry. In order to stop the Joker, we need to start to outthink him. Unfortunately, Harry and Hugo were never the brightest bulbs, so we need to smarten them up. Ever have to spend many hours trying to figure out your homework problems? Well, not anymore. With this new revolutionary technique, you will be able to turn hours of thinking into minutes. This process is able to work because acetone is an organic solvent, commonly used in nail polish remover. When styrofoam, or polystyrene, which is made of many hydrocarbon styrene molecules, is placed into the liquid acetone, the air pockets found in the styrofoam dissolve, leaving a solid a fraction of the size. This is due to the fact that both of these molecules are mostly nonpolar. Nonpolar means that they don't have a more positive or negative side of the molecule. Everything is balanced and symmetric. In chemistry, when molecules are alike in terms of polarity and mass, they will dissolve when put together. So when you take a nonpolar styrofoam and nonpolar acetone and you put them together, they dissolve. Now we can start to use our heads to defeat the Joker. Thanks for watching.
Absolutely stunning, isn't it, Dan?
Oh, it was breathtaking, good sir. But we need to find a way to burn the Joker's lair to the ground.
I think I have an idea, but we're gonna need Kendall and Annabelle's help to show us how they're gonna explode the Joker's lair.
Hello, I am Annabelle and this is Kendall. This experiment is called Popcorn Suds. In this experiment, we combine soap with hydrogen and oxygen in the form of H2 and O2. When these combine and ignite, they react quickly to form H2O, also known as water. A few words about safety. During this demo, we will wear safety goggles. Another important safety step is moving our bottle that is filled with the mixture away from the lighter. So before we light the soap, we will move the bottle away from us. We took this plastic bottle and combined hydrogen, oxygen, soap, and water in it. After shaking the bottle, bubbles form that mix with the H2 and O2. We then squeeze the bubbles onto our hand and then light them with a lighter. Because of the mixture of hydrogen and oxygen with the bubbles, hopefully a flame is produced. Our soap explosion is off to fight the Joker. Batman can simply put the soap bubbles on the Joker and light it on fire to explode on him. Thanks for watching our demo. I skipped some.
Wow, that fuel will definitely be helpful. So I think we're gonna definitely need more propane fuel.
Yes, sir, but our mole with the Joker just told us that the Batmobile is stuck in a cutting-edge device that is airtight, and we need a way to get out of that.
Sir, I think Chloe, Casey, and Jake's pressure fouling could probably do the trick.
Hi, my name is Jake. This is Casey and Chloe. I should probably be speaking to the mic when I'm saying that. We have a feeling that the Joker might have hidden the Batmobile behind an airtight safe. Lucky our pressure fountain can help us understand how to open any safe it might be hidden in. Here we have some boiling water. As we all know, boiling water creates steam, and this water gas is the key to help us understand how the container that holds the Batmobile works. We have also added food dye to help you see it better. Now watch as they flip over the boiling flask into the tub of cold water. The water gas vapor in the flask condenses to liquid to give us fewer particles in the gas phase inside the container. The flask then has a lower pressure than the ocean of air that we live in, and the air around us pushes the water into the beaker, up the tube, and into the flask. Steam from the boiling water gets trapped inside the flask and condenses, lowering the pressure significantly compared to the surrounding air. A fountain effect is formed by creating a pressure difference between the inside of the flask and the outside air, where the external atmospheric pressure pushes water up into the flask through a tube when a vacuum is created inside. Now let's see this on a bigger scale.
We live in an ocean of air. We live at the bottom of this ocean, and the particles of air are always pushing and bumping into us and everything around us. The water bucket below is getting pushed up into the flask by this ocean that we live in. The pressure inside the flask is lowered due to the condensation of the water gas. Now that the water is not boiling, the water particles condense and become liquid again, which is why the water boiling is key to making this happen. But actually, it is because the water is not boiling anymore, making lower pressure and allowing the air around us to make this awesome fountain, pushing the color water into the big fountain flask. Now that we understand how pressure works, no safe can stop us from getting the Batmobile back. Thanks for watching.
Wow, I knew Casey, Chloe, and Jake could do it.
Yeah, IG, but we don't got a way of getting in yet.
Well, please welcome Jamie, Kayla, and Faye for new smoke bombs for Batman.
Oh no, the Joker stole the Batmobile and we need to stop him. Let's use liquid nitrogen to create a big fog cloud so we can confuse him, sneak up, and get it back.
Yeah! While you may not know it by its name, this liquid is often used in the process of making your favorite ice cream flavors and pizza.
Whoa, pizza and ice cream? That sounds like a pretty cool date night.
So, we all know that liquid nitrogen smokes when poured. The fog that you see is actually frozen water vapor from the air around us. And if we add a liquid water to the nitrogen, much of it will flash freeze and we will see billions and billions of tiny frozen water particles, what you may know as fog. Faye, will you please add a nice warm cup of water we have to our fancy glass of liquid nitrogen? Let me get more. Okay. Wow, that was pretty good for the small cup we had. I think we can ramp this up to a pretty big scale. Over here, we have a big pail of liquid nitrogen, and we heated up about 1.5 liters of boiling water that Kaylee is going to try to pour in. We're going to try to dump it.
This should really rock if Kaylee can dump it in all at once.
To see Kaylee create a big cloud, let's all give her a countdown from 5. 5, 4, 3, 2, 1. That was awesome, guys. Now that the Joker can't see, we can surely get the Batmobile back. Thank you for watching.
Oh my gosh. Yes, we got the new smoke bombs for our gadgets. We'll definitely get the Joker with this.
The darkness will soon be over.
Oh, man. Oh, no, sir. I think Batman's getting emo.
All right, we're definitely need to get more positive if we're going to take down the Joker. So please welcome Grayson and Henry to keep Batman here alive and awake. Thank you.
Inside this tank, we have some hydrogen gas. Hydrogen gas is a great fuel for burning as its only products are water and energy. Hydrogen fuel cells are a great possible source of energy to replace fossil fuels as they release a large amount of energy and create pure water, and nothing is left over as a waste product.
We are going to encapsulate some hydrogen gas inside this soap solution. Since hydrogen gas is lighter than the rest of the atmosphere, the bubbles will rise. My assistant Grayson will create the soap bubbles while I'll attempt to light them. Please help us out because it is a difficult experiment to perform for 2 reasons. The bubbles like to pop before they get ignited, and sometimes the candle goes out before it can ignite the bubbles. Watch for the impressive display of energy released if I am successful in lighting the bubbles. So cheer loud if we're successful in igniting a bubble, and maybe we can even do 3 or 4.
Well, that definitely was enlightening and made me feel like I was in a state of enlightenment. Oh, wait. This isn't AP Euro?
Oh, man. Well, we can definitely use that H2 bubbles to distract the Joker's goons from the lair.
But we need more things. Do you think Romy, Mackenzie, and Alexa have a good elephant toothpaste reaction for us to see?
I think they might.
Hi everybody, my name is Alexa, and these are my partners Mackenzie and Romy, and today we'll be showing you our demonstration, which is commonly known as elephant toothpaste. You might be thinking, how on earth do you make toothpaste for such an animal? Well, with the help of a little chemistry, we'll be able to show you how.
To begin, we will demonstrate how to do this experiment 3 different times, and with each time we will change several factors to determine how concentration affects the speed of the reaction. In front of us, we have 3 beakers and various amounts of sodium iodide, water, alkanox powder, and a 30% concentration of hydrogen peroxide.
Hydrogen peroxide is a commonly known substance used for its bleaching properties in things like hair dye, teeth whitener, and household cleaning products. But today, we'll be using it for our elephant toothpaste.
For this reaction, any catalyst containing iodide ions will work. So we're using sodium iodide. When the reaction is sped up enough, it decomposes so violently that the oxygen and water will create a mixture and form foamy suds.
For our first reaction, we will be using 2 beakers, both filled with our 30% concentration of hydrogen peroxide, as well as the alkanox powder. Then to one of them, we will dilute the mixture with water. In doing so, they will form roughly about the same amount of suds, but we will show you how concentration affects the speed of the reaction. As you can see, like I said, they form roughly the same amount of suds. So now we're going to try the same reaction, but on a much larger scale. We'll still be using our 30% concentration of hydrogen peroxide, as well as our alkanox powder and some food coloring to make it a little bit more fun. As you can see, the 30% concentration of hydrogen peroxide when undiluted produces the quickest reaction.
Finally, as a fun experiment, we will show you how Batmole can use the suds to help him defeat the Joker by turning his own tricks against him. When you light a stick on fire, blow it out, then insert it into the suds of the elephant toothpaste reaction, it reignites due to the high concentration of the oxygen gas being released.
The decomposition of hydrogen peroxide produces water and pure oxygen gas, which gets trapped in the foam. Since fire needs oxygen to burn, the smoldering tip of the extinguished stick is still hot enough to reignite when exposed to this concentrated oxygen. Just the kind of explosive surprise Batmole could use to outsmart the Joker. Not only do I think this will certainly be enough toothpaste for our elephant, but hopefully we have inspired Batmole for some ways to help save Gothamville. Thanks for watching our demonstration.
Wow, these science ideas are giving us the best offense. But, as Obi-Wan once said, defense is always the best offense.
Obi-Wan? This isn't fiction. This is real life. It's not like we're trying to parody superheroes just for cheap laughs.
Well, sir, how about we have Elijah, Tyler, and Gonzo use their experiment to finally give us some armor for this fight.
Hi, everyone. I'm Aiden. This is Elijah, and this is Tyler. I'm assuming everyone here has used a balloon before. This one happens to be a plastic balloon. It's shaped a bit differently, but it works the same. They're quite simple. As you blow into the balloon, it starts to inflate due to the pressure inside pushing out on the balloon. Now, what would happen if we took a sharp object, like a nail, to the balloon? As you can see, it pops or deflates very depressingly, but that's okay. Now, if we increase the surface area pushing on the balloon by taking this platform and placing the balloon on it, what do you think is going to happen? It surprisingly doesn't pop, and this is due to the same properties that stop buildings and bridges from collapsing. The increase of area causes the weight of the balloon to be dispersed across the nails and no longer focused on just one point. Now we can use the same properties to get Batman some armor to help defeat Joker. As we will demonstrate now through the same properties that have stopped the balloon from popping before, we can do the same with a person, Tyler. His shirt's off. What a good looking guy. As you can see, he's able to lie on top of the nails, and we can even ramp up the amount of weight. Looks pretty heavy, but how do you feel, Tyler?
Feels kind of therapeutic.
I mean, that sounds good. Thank you.
Okay.
That was excellent. That's some great armor there.
Well, here's the deal, Danny. We still have a couple more experiments, so please welcome up Hannah and Lucy for their dill pickle experiment.
Woo!
Did you know the Batmobile is actually powered by pickles? It's quite useful considering it's both edible and affordable. Now you might be wondering, why a pickle? Well, folks, it's not just a snack, it's a conductor of electricity. This pickle will show us the power of the Batmobile. Hannah, please show us the electrical probes. Hannah. Thank you. A pickle is mostly water and salt. Water is a great conductor of electricity, and salt contains ions that allow electrical current to flow through. You can see the formulas of the ions on the slide above me. See the Na plus and Cl minus with little AQ symbols below them? These are the aqueous cation and anions that are inside of the pickle, and they are powering the Batmobile to travel at extremely high speeds. Now Hannah will connect the pickle to the electricity source, and that seals the deal. It's important to know that while the pickle might not seem dangerous, if you touch it while electricity is being conducted, you could be fried, just like the pickle. So, be careful. All right, if we can dim the lights and zoom in on the pickle. It may take a while, so be sure to relish the moment. As I said before, the ions conduct electricity through the pickle. These ions pick up electrons and carry them from one electrode to the other. As I said, this may take a minute or so, and I do have some jokes for you guys. How do pickles enjoy a day off? Yeah, they relish it, yeah. Yeah. What's a pickle's favorite show? Dill or no dill? And, okay, last one. How does a cucumber become a pickle? They go through a jarring experience. And this may take a little bit, but eventually you'll see it start to glow, and it'll look really cool. There we go. It's awesome. Behold, as we send electrical current through this pickle, now we can actually see the ions moving and creating a reaction, giving it a glowing orange color. Now we could power the Batmobile to catch the Joker. Thanks for watching.
Crispy. I think it's time for another chemistry joke already.
I think everybody's tired of it, but let's do it.
What? What did the proton say to the electron?
I wonder.
Why are you always so negative? I heard my grandpa laughing during that one. Now, we also need a visually distracting way to escape in our getaway car.
Ooh, Taylor Swift.
Not like the Taylor Swift song, but please welcome up Lucy and Ava for their kinetic experiment.
Woo. Hey guys, this is Ava and Lucy, and we're gonna light up your world. I'm sure the majority of you guys have seen glow sticks, and some of you may have been brave enough to heat them up. Today, you guys will come along with us to experience the glow of sticks throughout different temperatures. First, here's a regular room temperature glow stick, and if we could dim the lights, please. We will set this here in a cup so that you can compare it to the colors and intensities of the other ones that we are using. Glow sticks work because two chemicals, hydrogen peroxide and a solution of phenyl oxalate ester, mix when you bend the stick. The chemical reaction creates light without heat, making it glow. To start, we will put one of these glow sticks in ice water, about 0 degrees Celsius. You can see the reaction is much slower and the intensity of the reaction is less. Here's a normal glow stick in really hot water, nearly boiling. Check out the intensity difference from the room temperature one. And now we are emptying the contents of the glow stick into a test tube, and we will heat it to about 300 degrees Celsius. P.S. This is super hot. The most common reaction used in glow sticks is calcium with hydrogen peroxide. The energy from the reaction is given to a dye molecule, which forms the bright glow. There are many factors that dictate how fast a reaction takes place. First, surface area. Second, catalyst. Third, concentration. And finally, temperature. When you increase temperature, you increase the speed at which the reaction takes place. And when you decrease it, you decrease the speed. That's what we are doing here. In nature, you can see a similar reaction in how fireflies light up just as bright as our glow sticks. Thank you.
Sweet. Now, for the ultimate experiment, our magnum opus, we're going to need a big boom to finally end this madness.
Before we do that, we'd like to give a huge shout out and a huge thank you to Mr. Just. If everyone could please give him a round of applause. It is because of Mr. Just's hard work that we are able to be the successful students and the successful AP Chem show that we can, and we just couldn't have done it without him. Now, please welcome Nick, Colin, and Cole whilst they explode balloons. Forewarning, this is very loud, and you may want to cover your ears if you are sensitive to sound.
Hello, everyone. I'm Cole, and this is Nick. We will be looking at the science behind popping hydrogen in oxygen-filled balloons. What happens when you pop a balloon? When you pop a balloon, the rapid release of gas can create a sharp noise. The noise comes from the sudden expansion of gas into the surrounding space. Here, we have two colorless and odorless gases, hydrogen, which is highly flammable, and oxygen, which supports combustion. We are going to blow up a pure oxygen balloon, but because of the type of balloons that we use, it may or may not start on fire instead of blowing up. We are not going to do a pure hydrogen balloon because it does the same as a pure oxygen balloon. When hydrogen reacts with oxygen, it produces water in an exothermic reaction, meaning it releases energy in the form of heat and light. This reaction is a very explosive mixture with a 2 hydrogen to 1 oxygen ratio. When lit by a spark or heat, it makes a loud bang. This loud boom will scare off all the Batman's villains. You might want to cover your ears.
Testing. Yep. But before we finish, we want to thank all the real superheroes, all of you who are able to support us inside and outside the classroom. So, to finish, we'd like to give you guys 6 more big booms from balloons.
Boom, 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 boom.
Testing. Thank you for coming to the 2025 Lakeville South High School Chemistry Show. We hope you had as much fun as we did, and have a good night.
Thank you, Mr. Justice.